Let's talk about database indexing. You've probably heard of it, right? It's kind of the unsung hero behind pretty much every fast app you use. But it's also something that can totally make or break your system's performance. It really is the secret sauce for sifting through billions of records in just milliseconds. So what is it exactly? And how in the world does it work? Well, let's pull back the curtain and take a look.
So here's our game plan. First, we're going to tackle the big problem, trying to find a needle in a haystack the size of a mountain. Then we'll introduce the hero of our story, the index, and we'll peek under the hood at the brilliant little data structure that gives it superpowers. But like in any good story, there's a catch. So we'll uncover the hidden costs, go over some super common mistakes, and then finally, we'll talk about the real art of balancing it all out.
All right, let's kick things off at the very beginning, with a feeling I'm pretty sure we have all had.
Oh yeah, we've all been there. You're a user waiting for your feed to load, or you're a developer just staring at that dreaded spinning wheel of death. That frustrating, mind-numbing slowness, it often has a single culprit, the database, being forced to find just one little record among millions or maybe even billions with absolutely zero help.
This is the database's default method. It's pure brute force. Without any guidance, it has no choice but to do what's called a full table scan. Imagine someone told you to find a specific word in a 1,000-page novel that has no index. You'd have to read every single page, line by line. Now, for a tiny table, that's fine. But for a table with millions of rows, it is a complete and utter performance disaster. And this, right here, is where our hero finally enters the scene. The database index is the elegant, incredibly powerful solution to this whole brute force mess.
I mean, the difference in the approach here is just, it's night and day. A full table scan is slow, clumsy, kind of like just wandering around a city with no map. But an index lookup, it's direct, it's precise, it doesn't wander at all, it knows exactly where it's going, and it turns a marathon search into an all-out sprint.
You know, this is the perfect way to think about it, a library catalog. An index is basically a separate, super specialized data structure. It's like a sorted list of values, but each value has a little pointer that leads you directly to the full row of data. So instead of searching the entire library book by book, you just check the small, perfectly organized catalog first.
Okay, so this whole card catalog thing sounds great, right? But how does it actually work under the hood? Well, for most modern databases, the answer is a beautifully efficient data structure called a B-tree.
So what the heck is a B-tree? Well, it's a special kind of tree. You might be familiar with a binary tree, where each little node or branch has at most 2 children. Well, a B-tree node can have hundreds, and its whole structure is perfectly designed for how databases read data from a disk, which they do in chunks. By fitting a whole node into one of those chunks, it drastically cuts down on the number of slow disk reads you need to find anything.
Searching one of these things is incredibly efficient. You just start at the single root node at the very top and follow a direct path down. At each level, you make one single choice that instantly eliminates millions of other possibilities. You just hop from one node to the next until you land on what's called a leaf node, and bam, there's the exact pointer to your data.
And this is where it gets absolutely mind-blowing. This is the real magic. Because each node has so many children, the tree stays incredibly shallow or short. How shallow? Well, a B-tree that is just 3 levels deep can store and search over 300 million records. Just think about that for a second. 3 hops. That's it. 3 little jumps to find one specific item out of 300 million. It's incredible.
So, okay, indexes are amazing. They make our reads lightning fast, which, leads to a pretty obvious question.
I mean, if these things are so great, why not just put one on every single column in our table? Just index all the things. Well, like pretty much everything else in engineering, there's no such thing as a free lunch. There's a very, very important trade-off we need to understand. And here it is, the big catch. While indexes make reading data way, way faster, they make writing data slower. That means every time you do an insert, an update, or delete, you're not just changing the data in the table, you also have to go and update every single index that's connected to it.
Let's go back to that library analogy for a second. Every time you add a new book to the library, you don't just put it on the shelf, right? You also have to go to the card catalog and add a new card for it. Now, what if you have 10 different catalogs? One for the author, one for the title, one for the subject. You've got to update all 10 of them every single time. And that's exactly why having too many indexes on a table that gets a lot of writes can absolutely cripple its performance.
So this whole balancing act, this trade-off between read speed and write speed, it's really at the heart of every single indexing decision. And when people get it wrong, oh boy, it leads to some super common and really costly mistakes. So let's talk about what not to do.
Okay, here are the big four you see all the time. Number one is the obvious one, having no indexes at all, which we know is a disaster. But number two is the complete opposite problem, getting index happy and slowing your writes down to a crawl. And then you have numbers 3 and 4, which are a little more subtle but just as important, not using the right kind of index for the kinds of searches you're doing.
Let's get really specific with mistake number 3, because this one trips a lot of people up. Let's say you often search for orders using both the user's ID and the order status. Creating 2 separate indexes, one for each, is actually pretty inefficient. The database might use one or try to combine them, but it's just not ideal. A single composite index on both columns together is way more powerful. And here's the pro tip. The order of the columns in that index matters a lot. You want to put the column that narrows down the search the most selective one, first. And all of this, it brings us to maybe the most important point of all. Because understanding indexing isn't just some abstract technical exercise. It's a critical skill. It's one of those things that really separates junior developers from senior system designers.
I love this quote from a FANG system design interviewer over on Reddit. It just says it all. It's not about knowing the names of technologies. It's about understanding the trade-offs. Can you actually justify your choices? How is your database going to scale when it's getting hammered with millions of reads and writes? That is the level of thinking you need to build really robust, scalable systems.
So, at the end of the day, there's no magic bullet here. There's no one-size-fits-all answer. Every single application has its own unique pattern of reads and writes. The true art of database performance is analyzing those patterns and creating a deliberate, balanced indexing strategy, one that speeds up the things that matter most without totally crippling the rest of your system.
So I'll leave you with this question. When it's used wisely, an index is a hero, making your app feel instant and amazing. But when it's used carelessly, that very same index becomes the villain, dragging down performance and causing those frustrating delays. Are your indexes heroes or villains? The choice is yours.